Perfect. Hello everyone, I'm Ish and I'm a faculty at RPI. My advisor Dinesh Boradia during my PhD was supposed to be here. Unfortunately, he is not around, he couldn't come. So I'm here, I'm going to present pretty much the same talk. So this is the work me and my colleagues have been building for last couple of years at UC San Diego, where I graduated with my PhD last year before starting my career as an independent faculty at RPI. And here we are building real-time applications. We call it Edge RIC. It's a RIC, RAN intelligent controller, designed for edge applications, designed for real-time applications. And here I'm going to show you how we build it with srsRAN and a couple of other RIC which are designed for real-time applications. Like for example, Microsoft has project Jain, and we are collaborating with them recently, and we are building and integrating the different platforms together. So we have a unified platform for full capabilities doing real-time intelligent applications with the RAN, particularly with srsRAN. So what is the why we want to build a real-time application? What is the challenge there, right? So one, we want to support diverse set of applications, diverse set of users in diverse environment. And you can see we want to achieve low latency and high reliability for autonomous vehicles. We want to achieve these requirements for augmented reality, cloud gaming, and all these applications requires to meet a really tight deadline, have a higher data rate, higher throughput, high reliability. And these are diverse requirements for different diverse applications that we want to support with the next generation network for 6G, right? And all the application, most of these applications requires less than a millisecond tight latency while supporting these different diverse applications. So we know about all the network slicing and high layer functionality we create to achieve low latency slice and high data rate slice. But really we are talking about the physical layer that enables truly how fast you can process the data and you can achieve low latency. So all the 6G applications, they are edge assisted. Edge is helping these applications for real-time inference, scheduling, multi-user management, which user is getting which what resources, and so on. So it is really the edge network which has most of the control, most of the power to assign resources to different type of applications, different type of UEs. It could be AR, VR UE or IoT devices or different type of network devices. So how do we enable edge assisted assistance? So basically we have to build the RAN intelligent controller which are driven by AI ML pipeline, or they are optimized, and they are really optimized for edge devices, right? So we are envisioning building RIC. The idea is that this will enable building new AI-driven applications directly into the RAN. So far, we talk about non-real-time RIC or near real-time RIC, but they are really not enabling real-timeness, right? Because even if you have near real-time, that will be taking over 10 millisecond up to a second latency between RAN and the RIC controller. So these RICs are not designed for real-time applications. And our idea is, if you want to do most of the processing that happens at RU or lower DU, for example, the scheduling is done in some millisecond time scale. And for that, the existing RIC are not capable of handling any processing at the lower layer at RU and DU. So with that, the main issue is that for building such applications, the near real-time RIC could be more than 10 millisecond far apart, and the channel changes fast. When we talk about wireless channel, if you look at common mobility patterns, for example, if you are driving, the channel will change within millisecond, right? And if you are in a heavy multipath scenario, the channel changes even fast. So most of the decision like scheduling is taken based on the channel condition, but the channel changes so fast that if you implement any channel aware strategy into your near real time or non real time RIC, you are pretty much working with outdated channel, right? So for physical layer or MAC layer features in RU and DU, we need something which provide as updates as real time, as fast as the channel changes, so that we have the decision or new updates coming before the channel expires. So existing RIC cannot support these adaptations, and so we built Edge RIC. Edge RIC is a real-time RAN intelligent controller. It is built at the DU and CU level. It provides some millisecond control and latency. It can adapt to changing wireless channels, and it finally provides building intelligent applications using wireless channels with real-time control. So real-time control and telemetry is really important, and that's what we are going to emphasize on building this new RIC framework that we call Edge RIC. And the app that Edge RIC support, here we call them micro app. I think it is also commonly called DApp, and there are multiple common terminologies for it. I think we are still pushing for in the standards to create DApp or micro app to get into standards to generate more people to look into it, and particularly those working at the physical or MAC layer of network stack. It's an opportunity to start thinking about building such real-time applications. So one of the other issue that we notice in the RAN is the application agnostic feature of the RAN. Like, I mean, most of the optimization that we do in radio access network are not driven by application, or they are not very application aware. So we are envisioning RIC to have application awareness. Like when we talk about end-to-end application, we are talking about video streaming from a YouTube server or Netflix server, or anything which connects your end devices to support certain application. And here we envision the RIC as a platform to connect with the end devices. So if you realize the 7 layer of network stack, like we generally build each layers independent of each other. The application doesn't talk to physical layer, or cross layer optimization is extremely hard to do in any networking context, right? But we envision RIC as an enabler for doing cross layer optimization, to do application aware networking, and control of the scheduling policy can be controlled based on the application state of the video or XR VR application that you are talking about. So we want to inbuild and integrate this cross layer optimization with the platform that we are building Edge RIC here. So this is how this system architecture would look like. You see basically the RU, CU, DU on the left, and then on the right is our different kind of RIC which are tightly integrated together. At the bottom is our Edge RIC, which is building real-time applications, micro apps, and on top you see both near non-real-time and near real-time, which are also running xApp, and that provides, they are running in the cloud, they provide a data factory, they provide long-term model training and optimization, and they are tightly integrated with Edge RIC to provide real-time control. So we need to work across these multiple RICs, as well as the edge application which is sitting at the top in the right, which is also integrated tightly with the entire framework. So this framework allows us to be application aware by connecting the application server to Edge RIC, and it allows real-time telemetry, real-time control of the software stack. So our platform is application aware. It can handle real-time changes in the environment, real-time update with the channels, wireless channels, and it is O-RAN standard compatible. Right now it doesn't, O-RAN standard doesn't follow define for 5 layer, but the philosophy of the standards is being applied here, and a similar philosophy of xApp and near real-time RIC we are hoping will be adopted for the real-time RIC, and we are kind of following a similar philosophy to design our intelligent controller. So this platform is, there are multiple interests in building real-time control. Since 2021, you can see there are multiple platforms that have come up, starting with our previous demo in Mobisys 2021, and then DApps are coming from Northeastern University. since 23 has a lot of work. We had another Edge RIC demo in SIGCOMM. Janice from Microsoft, a project came up, Decima from Microsoft, Tiny RIC, which is from Nokia, talking about real-time control and telemetry. And then more recently, we are building a lot new application on top of Edge RIC, Beam Armor, Windex, and so on. I'm going to talk about some of these applications. So what is common here is all these different RIC, they might differ in their implementation, their architecture, but there is a single goal to provide real-time control of the radio access network. So two important RIC are can be highlighted. One, Edge RIC, what we have been building over last couple of years, and another is Janice, which is built by Microsoft. Most of you might already be familiar with the framework of Janice. There is a fundamental difference in the architecture of Janice and Edge RIC. Janice is based on building eBPF, like is more like an inline computing. Basically, you get information from the RAN in real time. It's super fast. You can even capture the raw IQ data from the RAN, and you can process it in the Janice controller. Mainly, they have demonstrated applications like real-time telemetry. You can infer a lot of physical layer application. You can monitor performance, power, and so on. But one of the drawback is you cannot have a real-time control loop, right? You want to build a control loop. You want to update the scheduling policy. You want to update a beamforming vector based on the analysis or AI/ML algorithms that you're running in the controller. So Edge RIC closes the gap. It provides ORAN compliant architecture which can provide a control loop with the RAN. So with tightly integrating with Janice, what we are hoping is that we will have the capability of streaming large amount of data that Janice provides and connected with the closed loop or control loop that Edge RIC has, and that will together will become a unified framework where you can have a large amount of data from the RAN to the controller, and then controller will have the AI/ML policy that will provide a control loop back to the RAN to upgrade your RAN based on the policy. So we'll talk about how these architecture work, and we'll mainly focus on the Edge RIC architecture and how it is built on the philosophy of ORAN compliance. So why do we need Edge RIC? I think this slide shows some of the results early on. These are reinforcement learning based scheduler that we built on Edge RIC to motivate that really, if you don't have real-time control, then building some of these applications would not have been possible. So you see, compared to near real-time RIC, if you build Edge RIC which provide real-time control, you can adapt to varying channel in real time rather than having tens of millisecond delay in near real time. Your Edge RIC provides much higher average throughput compared to other RIC which has longer latency. We are also showing we are training a reinforcement learning model, and the training is much faster. You can see the Edge RIC converges to the optimal throughut in just a few iterations, less than 10 iterations. But the near real time, even after like 50 iterations, it doesn't converge to the optimal value, and that's because the channels are really outdated by the time we get any control information from near real time RIC. So the latency is important. The latency between the delay between the RIC and RAN has to be minimal. It has to be below millisecond to really enable some of these optimal scheduling decisions that we are building. And similarly, you can see application awareness. For example, we are really focused on quality of experience, not just the quality of service. So throughput, latency are more like quality of service. But if you are really looking into the quality of experience that the user experiences, you need to look into the metric related to application. For example, in video streaming, the video stall duration is a quality of experience because the user directly experiences these things. And you can see the RL policy that we train in blue performs much better. It reduces the stall duration to below a few seconds compared to other scheduling policy that we apply at the same time, like max wait or max CQI. So it really emphasizes that machine learning or RL driven policies perform better than hard coding one of these scheduling policy from your dictionary, right? So all this is possible because we have a real-time control loop with Edge RIC. Edge RIC is not just for a single RL application. That's where it started the work from 2021 to 24 when it was first published. It was demonstrated with reinforcement learning based real-time scheduling. And then we have expanded this to multiple applications in security and privacy. Some of the work that we have done in MIMO RIC or Beam Armor, which provides interference-free multi-antenna beamforming system built on Edge RIC. I'm going to talk a little bit about that in this. We have built end-to-end energy optimization, and more latest work, Prism, is tightly integrating Janus and Edge RIC, and it provides more AI-driven optimized 5G stack. So we'll focus a little bit on Edge RIC, and then I'll talk about some of the other applications. So the RL-based scheduling, this is how we have built the pipeline. You can see the RAN stack runs an RT real-time E2 agent. This E2 interface is very similar to the E2 interface for near real-time RIC. We call it RT-E2 because it is a real-time E2 agent, which talks to the micro app on the other side, and it builds a real-time Edge RIC engine, right? And there is a bidirectional flow of traffic similar to standard E2 interface, where the RAN gets the data from the different RAN state. You get the information at the RIC, and then the real-time scheduling action will be passed from the RIC towards the RAN, so that RAN applies this decision. There is a data logger or Redis database that is being implemented at a higher order RICs, and then there is a near real-time RIC which has a training policy. So again, it provides 3GPP compliant control and data. It leverages RL for RAN optimization, and there is OpenAI GIM interface for having a large scale AI database that you can maintain for training and testing. So we built this RL based scheduling policy. It optimizes the quality of experience for the users which are connected in real time with the RAN. This is the working architecture of Edge RIC. So full architecture, you can see the RAN here, the Hi-Fi Mac RLC, these are the ODU that provides a real-time information exchange with the Edge server or the Edge RIC Edge controller, and then it integrates with the near real-time information at the core network, RFs, xApp, and application server connected together. And eventually the end-to-end application goes via the user and then the entire network stack. So these are the steps, like how it works. The RAN transmits metric to the RIC. Your RIC receives the states from the RAN without blocking the RAN. The RIC computes the beamforming weights based by training the RL agent, and the RIC sends these weights back to the RAN, and the RAN without blocking either RAN or RIC, it receives these weights from the RIC, and eventually it does the resource block allocation, or the scheduler allocates optimal resource block based on the RL policy. Eventually, if there is any changes in the state, the process will repeat. So this is how the end-to-end process looks like. It also shows the total latency that we have. All the tasks, all the 7 states are done within much less than 1 TTI, so that by the time the next TTI begins and you have next channel estimates and next scheduling decision you have to make, you will make it based on the latest channel information rather than relying on the old and outdated channel that you would have otherwise at non-real time or near real time RIC. So this shows the urgency or the real timeness of making these scheduling decisions and how you can update them based on the channel conditions and traffic conditions from each user. These are some numbers on round trip time. You can see the CDF of round trip time, which shows that as you increase the number of users, the overall latency increases, but then it remains within a few 50 microsecond, which is much less than a millisecond TTI. So even you can scale to hundreds of users while you will be able to support these policies in real time. So these are the latency in sending your data to the Edge RIC for your training your policy, and then finally based on the policy you will update your beamforming weights or update your resource allocation policy based on the RL agent in the Edge RIC. So it is real time, it is not blocking the RAN. We have experimented it over multiple different settings. We have mobile robot, drones, car, put it on turntable, and this will create a rapid variation in the channel profile, and which requires to update your policy really fast within millisecond time scale, and the results shows that. So I'll quickly show a demo of how these things work. And hopefully this can be played. Yeah, perfect. As you can see, we have 2 users which are connected to srsRAN running on 3 B210s with a 10 megahertz of total bandwidth. User 1 and user 2 receive iPerf data, which is creating the data traffic between the 2 users. And here you can see on the left the core network, eNode B, and the 2 users which are running there. And on the right, we are changing in real time different scheduling policies. So you will see right now the scheduler allocates half resources for each user, equally distribute resources to both users, and that works poor. But when we update the scheduling policy using reinforcement learning, you will see that in real time the throughput really goes up. So this is our RL policy, which is running with a fully trained model, and this provides the maximum throughput, total throughput between the 2 users. So this demonstrates that, and then again when we switch back to max weight policy, or when we allocate half resources to each user, then you see there is a degradation in throughput. So the best performance in throughput we can get by running our RL model running in real time, which is adapting to the channel condition, and it is providing the best throughput in real time. And all this, the entire control loop of Edge RIC is here running in real time without blocking the RAN. All right. So next we will discuss. We took this platform. It is really capable. It is open source. So if you want to try out different applications, you can build on top of Edge RIC. I will going to show a few more applications that we have built on this platform, and one of them is beam armor. So here really the idea is take the physical layer or high layer channels from the hi-fi information, right? And you can, if there is, for example, a jamming signal that you want to if there is a jamming signal in your at your base station, then it will affect the functionality of the base station. Like if you are trying to receive some genuine data from a genuine user in an uplink slot, if there is a jammer, then it will corrupt your signal. The base station will not be able to recover a signal from the genuine user, right? And it need not be a jammer. It could be an interference from nearby base station or any other devices, right? So a very simple policy like creating a null towards the jammer using multiple antennas could solve this problem, okay? But how will we implement this, right? So we built an app called Beam Armor into Edge RIC controller, and that creates a policy to update this app in real time, to update this beamforming policy in real time. So this is how it works. We have the Edge RIC controller, right? And on one side we are running it on srsRAN, which has E2 interface, RT-E2 interface with Edge RIC, and on the other side we have the Beam Armor app. We pass some of the information like the RAN configuration, MIMO channel, all the performance metric to the app, And the app implements a policy which creates a beamforming vector and many other MIMO applications like user selection or antenna selection or localization and tracking, so that the RAN can implement an appropriate beamforming vector to really nullify the interference, or based on the task or the application, you can build one of these different policies, right? So you can support many of these different applications and policies on Edge RIC. Without Edge RIC, you would be really looking into hundreds of thousands lines of code in srsRAN, trying to figure out where MIMO channels are extracted and how it works. With Edge RIC, you simply have one line to get all the channel information you need and one line to send your policy back. So your entire focus is on designing your policy rather than scratching your head looking into the large code base. We make this process simpler for you, right? So this is one of the policy. Very simply, if you have multiple antennas, you can create a null towards the jammer direction to nullify the effect of interference. We build this policy using Edge RIC controller. So on one hand, you stream the wireless channel, or in this case, we have been really streaming the IQ data from multiple antennas. If you have two antennas, Y1 from antenna 1, Y2 from antenna 2, you can send it to the controller. It will create a policy, it will create a beamforming vector alpha, and that will create your that will create the null. So if you have two stream, then simple applying the beamforming vector will create the beam nulling application. So this is how we did experiment with X310 setup. We have a base station or eNode B, we have a SRS UE and a jammer, and we will show that the system is capable. So without jammer, you see the SNR in blue is pretty high, around 15 dB, but when we turn on the jammer, you can see the SNR really goes down. The block error rate, initially it was very low, close to 0, no error, but then when you turn on the jammer, it goes down to around 50%, which is the maximum or completely random block error rate. You are completely losing your data and throughput. So we need something like beam armor in this case to nullify and see the how can you recover your SNR, or how will you get your BER back, how can you reduce your BER back to 0. So here is a small video to show how it works, right, and how we recover. So this is SRS eNode B base station and the user and the jammer. So it's working with 10 megahertz bandwidth, and this is srsRAN SRS LTE 4G version when we started this work 2-3 years ago, and at that time it only supported 2x2 MIMO. After this, I'm going to show with the latest 5G version as well that we made some progress in last 1 year. This is the jammer. It is implemented with a very simple Pluto STR with a couple of $100. You can buy these STR and you can create a jammer. So it is really a big threat. And jammer works in the same uplink frequency band so that it can jam the uplink signal at the base station. So here we are plotting real-time block error rate on the first curve, the SINR, signal to interference ratio, in the second one, and throughput in the third one. So right now nulling is not applied, so you can see the SINR is around 10, and when we apply the nulling in the beam armor, you can see the SINR goes up, your block error rate goes down, and your throughput is recovered. So here is what you can see. Roughly we can get 10 times higher SNR, and you can recover your throughput back to the original state as if the jammer before the like as if the jammer is not there, right? So you can really get rid of the jamming signal. So this is the work we did, and then we realized, okay, this was working with srsRAN 4G. We wanted to implement it with srsRAN 5G, which has support for 4 antenna. With 4 antenna, you have more degree of freedom. You can do beam nulling and beam forming at the same time. right? So we implemented the same thing with 5G version of srsRAN. We call it Beam Armor 5G, and this is how the interface looks like. You have 4 antennas in the receiver in the eNode B, and it has the Edge RIC interface based on 0MQ based PubSub publication and subscription interface, right, which is non-blocking interface to get the MIMO channel data from the RAN to the RIC, and then apply a MIMO control policy like your beamforming vector back to the RAN. And you can build multiple such MIMO applications running in this Edge RIC framework. And this is like a sister of Edge RIC we call MIMO RIC, particularly designed and built for MIMO applications. So previously you have seen 2 antenna setup with srsRAN 4G, and it was using raw IQ streaming without any sensing or and doing very rough beam nulling. With 5G we have 4 antennas, transmitter, 4 antenna receiver, and we can do much more. Right now we can, rather than just streaming raw IQ data, we have extracted the PU-SCH channel estimates from DMRS. These channels are across all 120 subcarriers, across all 4 antennas, across every TTI. This is a 3-dimensional channel matrix that we are streaming from the RAN to our Edge RIC controller to Beam Armor app, and it is creating this beam nulling policies in real time to feed back into the RAN. So again, there is a demo video for the latest version of Beam Armor 5G that we have built, and here you see in live action of srsRAN running on the PC. Now we are using N310, which allows us to connect 4 antennas at both transmitter and receiver. This is the jammer, same Pluto SDR, but with a power amplifier, and this is first time now we have taken it outdoor and we are doing some real outdoor test. The user is a standard Pixel phone that connects to the SRS eNode B. So you can see without jammer the channels are stable, the magnitude is flat and the phase is good, but when you turn on the jammer you will see that the signal really gets affected by the jammer, right? And here you can see when you turn on the jammer, the SINR goes down, your block error rate goes up, and your bit rate really goes down. We have already seen this, but again now we are seeing the same thing with the 5G version. Okay, so how we are helping here, we are showing how the jammer affects your performance, and this is where we have benchmarked the end-to-end metric. When you turn on your beam armor, how you can recover back. So on the first figure you see the green bar is the baseline. This is where your SNR is without any jammer. When you turn on the jammer but you keep your beam armor or BA off, you see the SINR goes down to 2 dB, which is like 10 dB lower, right? But if you turn on the beam armor, you can see you can really recover back your SNR to the original level. The median value is same as the value which was without jammer. So despite having the presence of jammer, because we are able to do real-time update in our policy, we can adapt to the channel from the jammer, we can do jammer detection and mitigation, and using the real-time update coming from the Edge RIC, we are able to recover the effect of jammer. So this is one of the few applications. You can do jammer mitigation. You can build another application for sensing. Because we have multiple antennas, you can locate the angle of your user devices based on at what angle the signals are coming from using multiple antennas, and we got really good accuracy. Like the accuracy for localization is around 2 to 3 degrees when the angle is close to 0, and when the angles is little far apart around 40-50 degrees, then the accuracy is also good enough, around 7-8 degrees. So this is good. You can start thinking about building more sensing applications on top of this. The latency is not high. We have shown the previous example of latency with Edge RIC. Here, if you see the latency numbers with and without GMQ streaming. So if you run srsRAN without any of the extra code that we have written for Edge RIC, it takes roughly 1500 microsecond, but with GMQ streaming it is going to around 2000 microsecond. So roughly the delay is around 100 to 500 microsecond that you are adding, which is still much less than a TTI. So the RAN still works in real time, it updates in real time, and it is able to take the policy from Edge RIC or the app that are running in Edge RIC and run it in real time. So yeah, how am I doing on the time? It's good. Okay, so I think I'll just conclude here then. I have some backup slide, but I think this is good enough to take some questions, and I'm happy to discuss more if you're interested. Yes, please. Does Beam Armor works with 7.2 split? So right now we are working with full srsRAN, but the answer is yes, it will work with this split, because we are looking into the beamforming or scheduling decisions which are part of DU. So it will work with any RU out there, which, as long as it provides the channel estimates to the DU for implementing the beamforming policy and the entire scheduling framework which is available in the DU. So we are envisioning this as a framework which can integrate tightly with your DU, and it has access to channel and scheduling policies. Yeah. Yes, please.
That's great. I don't know too much about the node steering, but just curious, is there, and I don't know if there is, but because the VLER right after you did the node steering, when you change the antenna, kind of change the antenna pattern, is there an issue with the group delay? And not just the sign ramp?
So when we switch the antenna, when we use when we create a beamforming vector using multiple antennas, the question is there a group delay?
Is there a change in, like phase response of the antenna system that might affect I imagine that might affect the OPM.
So there could be some artifact from the antennas. If you have seen the setup, we use the antennas λ/2 apart, which helped us to remove any coupling between antennas or like any extra delays from antenna. But some of the hardware artifact could be there. But despite them, the beamforming policy or beamforming vector is independent. Like, it applies to the antenna as long as they are λ/2 separated. We can do sensing and angle estimation, and as long as we have the channel, real-time channel estimated from the antenna, that will capture the effect of any hardware artifact, and it will the beamforming or beam nulling will null or try to null the artifacts, right? So yeah, we have seen that with a realistic setup it works, and we haven't gone too deep into like really optimizing the hardware. Like, we just use some of the commercially available antennas and kept them λ/2 apart for this setup. Yes.
Sorry guys, I'm going to have to cut now with our next speaker, but I'm sure if there are any other questions, I should be happy to take them during the coffee break. So thank you.
Perfect. Thank you very much. Yeah.
So next up we have discussing debugging TCPs.